Hello, my name is Aitor Artola. I'm going to present our work, GLAD, a global to local anomaly detector. Industries are looking for automatic solutions to control the quality of their production. The solution must be robust to ensure a low number of false alarms and general so they can be used for any object without changing the method. Classification is not appropriate because the anomalies may be few and statistically inconsistent. Unsupervised modeling methods are a more general choice because they do not require anomalies. They are theoretically able to detect new kind of anomalies and they produce a measure of normality. Before talking about the modeling, I will talk about the pre-processing. For rigid part with an alignment with inverse compositional algorithm. This alignment introduces the assumption that a specific position in the image corresponds to a specific structural element on the object. The second pre-processing is common in the state of the art. Rather than using images, we extract features from the different layers of a neural network pre-trained for another task. The intuition is that the first layer are compressed and semantic descriptor of the image, which are not dedicated for the task for which the network was initially trained. We have chosen to model these features via Gaussian mixture. This type of density is suitable to estimate how multimodal data populate the data space. To go into more detail about the estimation of the model, we wanted to learn a localized model to take advantage of the alignment, but we also wanted to take advantage of the quantity of data to better estimate the covariances. The solution we propose is a global to local mixture described in this scheme. In the first step, the mixture parameters are estimated globally without any localized information in order to estimate the Gaussian parameters. We then localize the model by learning the weight locally, which require less data to be estimated correctly. The parameters of the Gaussians are fixed and only the weight map is estimated. This map is often sparse, which means that even if globally the mixture has many Gaussians, few are used at each position. For the detection, we have a mixture per network layer. To test a new image for each layer, we estimate the probability map, and we merge this probability map using a product. This fusion is equivalent to consider that the layers are independent in probability. Rather than scoring it with the worst probability, we use a Q-quantile, which was more robust to false alarms. In the ablation study, we have studied the impact of many parameters. A part of this study is exposed in this table. Most of the experiments are done on MVTech ad database. The impact is shown in speed, weight of the model, and area on the ROC curve. We tested ResNet 18 and ResNet 15 for representation. ResNet 15 give a better detection result, but is also slower and heavier. The regularization we have chosen allow to K-MLE to be as good as EM, while K-MLE train faster. The localization of the weight allow us to improve the area and the ROC curve of 1%, but also reduce the inference time and did not make a so heavy model. Our method gives state-of-the-art result. The improvement is mainly on MVTech objects rather than on textures. Our method is more suitable for objects that have fixed and localized structures. Our results on texture are not the best, but they are comparable to the state-of-the-art. Our method outperformed PADIM, which use a Gaussian by position as a model. This shows that even locally, the features that are multimodal. The sparsity of the model allow GLAD to be as fast as PADIM, while it is a way more complex model. This is all for my presentation. Thank you for your attention.